Hello. Hello, everyone. Hello. Before the session starts, I want to make an announcement because, as you may know, tonight is San Juan's night, and we will try to make a bonfire in the beach. So, if you want to come with us tonight. We will meet here at EDEM, at the door, at 8, and then we will go all together to the beach because some of us, of the organizers, will be there and making preparing the bonfire. And just to say that. Please don't bring your bag with the laptop to avoid problems with people. And also, I recommend to you to I don't know, like manage your drinks and food for the dinner and so on. Okay.
Okay, so now we have an invited session. I hope you can concentrate after the bonfire news. And we have Manuel Fernández Veiga. He's a full professor at the Universidad de Vigo and also a member of the Atlantic Research Center, where the Vigo Quantum Communication Center is located. Además, besides, he's the coordinator of the Masters in Quantum Technologies that is in the universities of Galicia. And his research in quantum focuses on quantum networks, which is the intersection of network engineering with quantum communications and information. And particularly, he focuses on network architectures and also in hybrid classical and quantum networks. So, Manuel, thank you for being here with us, and whenever you want, the floor is yours.
Thank you, Angela, for this introduction. I'm very pleased and I'm very happy to be here today among such young and talented people because for one reason, this is quite striking for me. I'm definitely not young, as you can see, and not 100% of the time I'm a full researcher. And besides, I don't speak exactly the same language as physicists because I'm an engineer by training. So my goal today, that's why I'm telling this foremost and before starting the presentation, is to trying to convey my goal today in this talk, which is a long talk, is trying to convey you the idea of how a complex system like a network can be built using the pieces that you already know, using the quantum science and how can we convert or transform the quantum devices and the quantum science into quantum technology on a large scale. Because one thing is doing things in the lab, this is fun, playing with devices and designing experiments and measuring things, and a completely different thing is trying to implement those ideas and those physical principles on a large-scale system, on a nationwide network, on a regional network instead, and for millions of users. That's the ultimate goal of building a quantum network. And my second goal today is trying to introduce the idea that quantum networks are more than just communicating information or transporting information from one point to another point. Quantum technology introduces different aspects into how we conceive and how we operate networks. So this presentation is not highly or deeply technical. In fact, it is the opposite. Most of the ideas are quite elementary and straightforward, but you should have in mind that the challenges for building a large system like a quantum network lie onto the hardness of integrating all the pieces, all the components together and making them work at a manageable size with a manageable set of operations. So the talk is organized around these 5 points. We will review some basic quantum networking principles at the very beginning. We will move next to understand, that's not the correct word, of course, to review why entanglement is the fundamental resource for building networked applications and networked systems. Then the middle part, and maybe the largest one, is about how to use classical resources for quantum networks. In other words, how to adapt the classical networking technology or engineering networking technology for quantum networks. We will review in the fourth part 2 examples of wide area terrestrial and non-terrestrial satellite quantum networks. And finally, some concluding remarks which bridge the gap between quantum physics and wireless communications, specifically how to use Rydberg systems as antennas, besides many other applications that these systems could have. I almost forget to tell something about myself and why I'm here today. So I will use just 1 minute for that. Yes, I'm Manuel Veiga. I'm a professor at the University of Vigo. I'm not the full coordinator of the master. I'm just the local coordinator, which is much more modest. But anyway, I manage some procedures within the master, which is a joint effort among the 3 Galician universities, La Coruña, Santiago, and Vigo. And I'm seeing here some familiar faces, by the way. Not many, but just a few. And my training, as I said at the beginning, is a communication engineer, which is a mix of electrical engineering and computer science. Spain is a little bit different in how to structure this discipline and this field. For many years, I have been working and doing research in networking for wired and wireless systems. And at the same time, I was in charge of teaching classical information theory at different levels. Some years ago, we discovered quantum principles and quantum technology, and I became interested in quantum information theory and also in quantum error correcting codes. And all of this converges into applying this knowledge into quantum networking. So in some sense, in a certain perspective, I'm a newcomer to quantum technology also. Well, that said, let's go through the first part, the main or the fundamental quantum networking principles. Well, in a nutshell, the idea is that a quantum network is not only about, or not just about, moving bits from one point to another point. That's the task, the main task in classical networks, because bits can be copied at no cost for free and can be moved at a very low or cheap cost. However, for classical networks, moving bits is not the complete story, because those bits, ones that have been copied, have to be coordinated. The copies have to be made consistent. In contrast, at least in my understanding, for a quantum network, we need to go beyond this idea, not only because copying information is not possible, but because many of the fundamental quantum information processing tasks are distributed in nature, are inherently and intrinsically distributed, like sensing at different points and combining those measurements, or like computing. Distributed quantum computing is, of course, the main foreseen application for building an effective network. Also for communications, quantum key distribution is the most mature and the first success of quantum technology, but also for implementing quantum protocols. By this name, I'm referring to the extraordinarily large zoo of distributed tasks for processing different quantum states at different sites and different places, and fulfilling complex tasks. For instance, strange or weird things like quantum money, quantum Byzantine agreement, if you know these terms, achieving consensus in a distributed network, and so on. This talk will not focus today on quantum protocols, because we have so much material to cover, just speaking about communications and sensing, and a little bit, not very much, about computing. So a future quantum network, which is still far in prospect, because technology exists, but there are quite a few challenges for implementing or for realizing complete network includes all these 4 axes, or all these 4 dimensions. Not only moving the qubits, that's maybe the simplest task, if I can say this, but also to be able to solve with local operations, sensing procedures, distributed computing tasks, and implementation of practical quantum protocols. So this is a timeline of major milestones and achievements in quantum networking and in quantum network technology, starting back in 1997 with the first demonstration of a photonic quantum communication. Of a photonic quantum communication in networks. Well, the timeline distinguishes between theoretical advancements, prototype or laboratory implementations, and landmark experiments. Of course, the history is not very long. It lasts for almost 25 years, approximately, and it's not the end in 2023. A couple of milestones have not been included here in this diagram, but you can review quite easily the major achievements from lab to systems that demonstrate in a practical and feasible way what can be done and what cannot be done. Concerning transmission of quantum information, specifically, you can see in this right part of the timeline that, both terrestrial communication and non-terrestrial with satellites communication is possible on a very different scale. For terrestrial networks, we know today how to generate and transmit entanglement through a few tens of kilometers, maybe longer. I will speak about this just in a minute. For terrestrial or satellite networks, much longer distances are possible with a different kind of technology and because of different reasons. Not all these landmarks points deserve a specific comment, but the idea is that if you review just how this progress is going on, there is an active area of research, of applied research, which is still in its infancy. Most of these milestones are quite modest so far and do not allow for now to build a fully operational network, and that's something in debate. It's questionable whether a real network with the same functionality and the same operating principles that we understand today can be done in the next decade. However, technology is extremely is an enabler for this idea. Another look at how technology, quantum technology, may enable building such a network is to understand what we can do today and what we need to do for implementing this in reality. So this plot and these figures depict the current position, the area of NISQ computing. I don't need to explain this, I guess. And different forms or different metrics of measuring the quality for communications in a network or for sensing or for doing some kind of computing. While we are still today in the lower left end of the left side plot, we would need to advance to much more reliable systems, much larger systems. And this is an important idea, both parts at a time. Not only more qubits and more reliable qubits, but also a fundamentally different and larger scale of the whole system. So this is not about putting more qubits into a single device. It is about connecting many millions of those devices together to form a new, different system. The table here presents, among many other possibilities, different metrics or different measures of how to understand complexity in networks. Speaking of quantum volume, the number of physical qubits, the number of logical qubits, which is currently very low, tens, well, not so low, but not maybe a couple of order of magnitudes larger than that. But we will need much more than this, in the order of not only thousands, but tens of thousands and hundreds of thousands logical qubits for implementing some tasks. Gate fidelity is high, but we need another 9 and possibly another 9 in reliability. And especially, we need to improve significantly and very substantially the coherence time of quantum memories, something that I will explain in a later slide with much more detail. And of course, to extend the entanglement range that is achievable today with the technology that you have mastered in your degrees. The lower part of the table shows how we can measure quality for those systems, for communication tasks, for computing tasks, and for sensing tasks. And the most important part in this formula is the dominating factor. For instance, for communication, the squared factor is the number of logical qubits. So improvements in the number of practical logical qubits pushes up the quality of any communication task, and so on. The rest of the factors appearing in the formula are linear, are only two quadratic terms, and this should enable us to shift to the top right part of the graph in who knows how many years. That's part of the uncertainty and depends strongly on how the fundamental technology is being developed. This picture is a little bit outdated. Quantum key distribution, as you know, is the most successful so far practical implementation of quantum technology. It's about creating a secret and information theoretically secure secret among two parties with no trust initially between those two parties. Even if the information is not accurate and exact, well, it's no surprise for anyone here that the world is rushing for building a mature and large quantum key distribution network. Not only a point-to-point network, but a multi-hop with different number of nodes and across or throughout all the world. The different efforts also reflect or show different investments into this field and how the different technologies that for quantum key distribution specifically exist find their place into this landscape. In particular, the different implementations of discrete variable or continuous variable quantum key distribution systems. In Spain, which is not included here, the Madrid network. From 2018, well, the Madrid network, maybe some of you know many more details about its structure and operations. It's a metropolitan area network with roughly a dozen nodes, not only 3 nodes, as suggested by the icon. And it's run by different companies and different institutions. And the most interesting information about the Madrid network is that among all the examples included here, it's a heterogeneous network. It is composed of different QKD systems, continuous and discrete variable, and different manufacturers. So it is in itself an exercise of integrating different pieces of hardware into a single system. The achievements are quite remarkable, not in the secret key rate, 20 kilobits per second is low for any realistic application. Today, it's larger than that. And the coverage, it's around 30 kilometers, is typical of a metropolitan network. I will give you more examples about implementations for quantum key distributions and other ongoing experiments later on in this presentation. So, what is the current situation? Where was the point we are regarding the different contributions that can fuel or push quantum networking in the next years? For me, we need to highlight these 4 different areas. So there has been some success, quite important, about distributing, about generating and distributing entanglement between remote sites, from one sender to a remote destination, typically in single link systems with dark fiber or not, maybe sometimes in compatibility with current telecommunication networks, which is a different and complementary major challenge on itself. And however, the rate for entanglement distribution should be increased if we want to use for something particularly useful or beneficial these networks. Concerning the entanglement generation rate, I mean the sources of entanglement, with today's technology, we can generate with not much difficulty, rates around the kilohertz. And with some special hardware, we can move up to gigahertz. However, this is insufficient. Again, for building large and complex networks, we will need even more or higher rates for generating the entanglement. And this is because entanglement as a resource has a very low efficiency when we try to create the entanglement end-to-end with highly enough fidelity. Again, I will explain this in more detail in this talk. A fundamental technological barrier for building a network is the manufacturing of good quantum memory units. If we want to mimic or replicate the fundamental principles, the fundamental operating principles of a classical network, we will need to build some devices, repeaters or switches, which inside use memory, the ability to store qubits for sufficiently long time in order to perform swapping and expand the reach of entanglement. Well, today's technology is incapable of storing a qubit, whatever its physical form, more than a few milliseconds. Only with some exceptions, longer coherence times and longer persistence times are possible. And a fourth technological barrier is that we need even more advances in generating bright and indistinguishable photons. Just the pure creation of qubits needs further improvement. So let's go through all of this. Let's examine next the principle, the major quantum resource, which is used in a network differently, in a quantum network differently from classical network. This resource is, of course, entanglement, the capability of generating entangled photons of high quality. Generating the photons entangled is not enough, by the way. And with this, we want to imitate, to apply exactly the same idea upon which the classical internet works, which I'll review just in a moment here. As all of you know, in internet, bits are moved hop by hop from one point to the next point, are stored temporarily in a buffer in any intermediate point, and then are forwarded to the next point. And this is repeated as many times as necessary until a full path from the source node to the destination node is covered. So storing, the ability of storing the qubits for applying something similar to this store and forward paradigm is what we seek when we speak about a future quantum internet, possibly, because other principles for operating the network are not so clear. Let's go step by step about what these quantum resources can provide and what cannot provide. I do not feel very confident about this kind of material on physical devices, so please forgive my sloppiness in presenting this idea. If we first examine how to generate entanglement at a given point, well, the two major technologies that exist today, as far as I know, are the spontaneous parametric down conversion and using quantum dots. Both technologies are complementary. They work on different ranges and based on completely different physical principles, but they complement each other and they find different ranges of applications. So for spontaneous parametric down conversion, an input signal is passed through a nonlinear crystal, nonlinear optics, and the desired signal can be extracted. And just the idler is dismissed. The basics for quantum dots is totally different. This is just semiconductor technology, which is based, which can operate in two different regimes or based on two different ideas. One, it's a cascaded emission of photons, and the second one is a direct, spontaneous two-photon emission, which is more in vogue today. Well, I will not go deep because my knowledge is insufficient for explaining this into the details of how these devices, what are the advantages or the disadvantages. But however, in the radar plot here, you can just observe the main features, the main characteristics comparing what can be done with one type of device and what can be done with the other type of device. Perhaps the major difference between the spontaneous parametric down converters and the quantum dot entanglement sources has to do with determinism or probabilistic behavior. Because the parametric down converters are probabilistic, while the quantum dot technology is deterministic. This is not the only difference, but it's fundamental for quantum networking because we engineers or network prefer much better determinism over any sort of randomization. Probability is a mess when trying to operate really large systems. So sometimes we can extract good properties of large probabilistic systems, but most of the time, introducing stochastic or randomness or some probabilistic behavior is very difficult to handle. More examples of this will follow today in this talk. Another dimensions of the comparison of the radar system, the radar plot, are not so clear. They don't show a clear winner on entanglement fidelity. With both systems, you can achieve exceedingly high fidelity values, well over 99%, which are good for quantum networking applications. A very good brightness, some advantage for quantum dots in this case. And for scalability, for building many devices and apply this into different systems, maybe spontaneous parametric down converters have a little advantage over these parts. Well, that's almost everything I have to say about how the entanglement sources achieved today and what can be done. Even though the plot suggests that quality is enough in brightness and in distinguishability, this is not the true story. We still need more brightness and more indistinguishability properties for enhancing these sources to be able to use it in extremely large systems. If we speak about quantum memory, the hardware for building quantum memory units is very, very diverse and very varied. There have been attempts for building these memories with all the possible physical systems that you could imagine. This table, which is also a little bit outdated, sorry for this, summarizes the current performance for building quantum memories, what can be done or what can be achieved, and under what conditions. There are up to 7 different hardware platforms for building a quantum memory, starting from atomic ensembles up to using rare earth systems for storing qubits in different forms. From all the figures in this table, if we look at this with an engineer's perspective, the most interesting part, yes, the most interesting part, perhaps not the most important part, is the last column, which is the wavelength that naturally describes the system. Why is this important in the case of quantum networks? Has anyone the answer? Yep.
So it is compatible with the existing infrastructure?
Yes. We look for systems, we crave for systems that are perfectly compatible with the current telecommunications infrastructure and for transmitting light through fiber, for optical fiber, we only need, we have to use 3 specific windows for the wavelength. The most popular one is the C band. It's 1,000, or it's around 1,500 nanometers. So if we can build a memory or a source which is naturally compatible with that wavelength in the C band, that's perfect for our needs. If not, we have to do complex frequency conversion, and difficult, and not so efficient in most of the cases. And the second most important figure in this table is about the persistence times. The T2 in this first block or in that second block. That depends on the differences whether we are looking at specific quantum memories or we are trying to entangling and storing 2 separate quantum memories. Anyway, regardless of this difference, most of the times, the time scale is around microseconds or milliseconds, with a couple of remarkable exceptions. That's clearly not sufficient for storing the qubits in memory, in a repeater or in a switch. Because typically, the local operations to be performed inside the repeater and the switch require longer persistence times. Doing a swapping entails few elementary operations, which require or is greatly facilitated if the persistence time is much longer than this, at least 1 order of magnitude. We should look toward persistence times around the scale of seconds, at least. Of course, we're not looking just unerasable memories like electronic memories, of course, but persistence time of seconds would be a great advance in this field. Well, networks will be built using intermediate devices, which are called repeaters or switches. If you know how a quantum repeater works, I will skip this part. If not, I will review quite briefly the essential and the key operation in a quantum switch or a quantum repeater. The only purpose of a quantum switch is to propagate entanglement from a local area to a longer line. So the idea of entanglement can be seen as a generalized teleportation. Forgive me if this is just a loose comparison, but in the end, it's just a generalized teleportation to adjacent systems, which initially share 2 different entangled pairs, can be converted into 1 single system with an entangled pair of photons between the very end, the first one and the last one, just by applying a Bell measurement at the intermediate point. So if we start with 2 entangled pairs between systems A and B, 1 pair, and systems Z, D, the second pair, and if you apply a Bell measurement onto systems B, Z, the final outcome is an entangled pair between systems A and D. This idea is simple, but it's absolutely powerful, because if you repeat this idea over and over, the reach, the extension of the entanglement can be propagated theoretically to any distance that you could need or necessitate. So this diagram represents how entanglement works in a general case. In this case, in a 4-hop system with the initial pairs already created, just a first operation of swapping entangles the dotted boxes, and a second swapping operation creates the final and target entanglement between the left end, the green dot at the left part, and the green dot at the right part. This has to be repeated, as I said, as many times as you need for creating a path, where a path is just an entanglement relationship between 1 source and 1 destination. Well, the terminology is not very correct here. Speaking of source and destination, because the 2 parties are completely symmetric, it's not very precise, but well, it's just a loose idea. The engineering problem with swapping and with entanglement is twofold. First, entanglement is swapping, is probabilistic. So sometimes it fails with a significantly high probability. This means that it has to be restarted again if you want to build the end-to-end entanglement. For engineers, this means wasted time and wasted resources, and not sporadically, just continuously, and a lot of resources. Secondly, it also disturbed by loss and attenuation. In addition to being able to perform effectively entanglement swapping, we want to do this with high fidelity photons. But along the path, fidelity decreases and gets worse. Many expected quantum future applications require extremely high fidelity pairs to be effective, not the least distributed quantum computing. So it's very important not to lose this fidelity or to restore at some point in the intermediate path, if we are able to do that, a sufficiently high fidelity. In general, there are many different forms of achieving or performing entanglement swapping, but it requires a minimum number of swaps, one at every intermediate point. And the hidden assumption for doing the entanglement swapping is that if this is not to be done synchronously, with all the nodes perfectly synchronized to apply the operations just at the right moment, then if we want to implement this idea of entanglement swapping asynchronously, just when resources are available at the nodes, we need to store the qubits at the intermediate points until the system is prepared to perform the swap. So memories are fundamental for this idea, and if memories do not have enough quality, well, the whole system is not feasible at all. This circuit is the typical circuit representation of the entanglement swapping operation, just the same as we saw conceptually in the last slide. So this set of operations admits or can be described with the language of quantum circuits, just using the three parts: the generation of the pairs, the specific operation of the quantum repeater here at the middle, and just the final outcome, which is the entangled pair between the two endpoints. Another view of how entanglement swapping can happen in our network is just this abstracted representation. In the top panel, just two sources, S1 and S2, generate two pairs, or two qubits. One is the control for a logical network, for a logical gate, sorry, and the second is the target qubit. This picture highlights the necessity, that's why I included this part into the slide, highlights the necessity, the need of using classical communication for guaranteeing that the swapping has finally achieved the expected result. So it is not only about doing local operations or just manipulating the qubits, only that some additional classical protocol for synchronizing the information between the one part and the other part seeking the entanglement processes is completely necessary. A straightforward implementation with linear optics of the entanglement operation is represented in the low part of this slide. I believe this is pretty clear for most of you. What is the current technology with repeaters and switches, and what is the ultimate performance measure about end-to-end entanglement swapping? Well, I tried to summarize these ideas into just a single formula, even a simplified description, and a table. We can classify these ideal devices, quantum switches and quantum repeaters, into generations depending on what kind of procedures they could use to overcome the errors and the loss. So first generation switches and repeaters deal with probabilistic errors and with probabilistic operational errors too. Have a time scale given by a simple formula. I will not go into the details. I have a polynomial complexity in those operations considered globally. Second generation quantum switches and repeaters will handle probabilistic loss, and deterministic will correct errors with deterministic procedures. That's the main difference. They have approximately the same time scale, but with an important difference. In the time scale here, the length is the distance between two adjacent or consecutive repeaters, not the whole length of the path. And complexity is lower, is polylogarithmic. And in third generation, which do not exist yet, repeaters, both types of errors, due to loss and due to operational errors, will be corrected or mitigated with deterministic procedures, and complexity is approximately the same. For us, for designing a network, the formula given above is more important than the generations or the classifications. This taxonomy is only useful for memorizing things, but not particularly informational beyond that. But the formula above, all the terms are not important here, reveals or shows that the expected end-to-end time for creating an entangled path in a network grows exponentially, roughly, with the number of nodes, because errors fall back all the procedure and has forced us to start over again. This exponential dependence is quite clear, appears in the numerator in both terms. So the number of hops appears in the product, in the fraction, and also behind. And what is hidden in this formula is the idea that once an attempt to create an end-to-end entanglement fails, all the resources involved into that operation are completely lost. They cannot be reused. Well, this is quite obvious. So we will see how to handle this idea of errors and what they could, how they could be solved. But before reaching that point, again, this table shows, well, this type of optimistic predictions that engineers like to do about when technology will exist and what steps are necessary to reach that point. So take this with some skepticism, please, because this is only a hint about, well, when these things will exist, or to be more honest, when some people believe these things should exist. This refers specifically to QKD, quantum key distribution networks, but the prospect can be applied as a blueprint to general networks as well. So here you can see a lot of intermediate steps. Building photonic QKD chips, for instance, instead of large heavy boxes and very noisy, by the way. So miniaturization as one of the first steps. Are we close to that? If anyone has the answer, please raise your hand. And similarly for the standardization efforts, certification efforts, for non-lab early demonstrations of building QKD networks on the space with effective satellite links. Only a famous experiment exists to date. And making all of this technology, again, this is a repeated idea along this talk, compatible with telecom networks. Nothing of this is really useful if we cannot integrate the technology into existing networks, because it's out of any idea to replace completely the current technology in a network with a new one. That never happens, believe me. It's absolutely impossible. And if you want an example, even a classical one, maybe you did not notice that the current internet works pretty badly at some points. Yes, it's not working properly. Well, this may be not noticed as a final or end user, but the inner working of the internet in many parts is not good. The reason is not that the classical internet has not been designed correctly. It was. And the creators were visionaries, almost. However, they couldn't imagine the scale that the network took over the years. And they were naive when creating the technology. They designed the network for a very different world that our world today. This can happen again with quantum networks. So we can design a system which is perfectly sensible with our view today, which is not good for 20 or 30 years in the future. Why has the classical networking technology not been replaced so far? Because we would need to create a new network from scratch. Out of sense, completely. So this lesson is more important than it appears. So networks evolve, they are not replaced. So technology is continuously updating how the devices and how the system works, but never substitutes completely any previous generation. And this is not only for business reasons, it is for perfectly logical reasons. So given this commentary part, let's move to the next part that we need to solve, that you need to solve to build that network. How to deal with errors, what to do if errors happen when performing any sort of operations. So there are many different forms of handling error mitigation and error suppression in quantum systems. I'll start the description speaking about probabilistic purification protocols. I insisted previously on the idea that for many end-user final applications, like in distributed quantum computing, having high fidelity entangled photons is a necessary condition. So in addition to swapping, creating that entanglement, what can we do for increasing up to the threshold that we need the fidelity of some qubits, some entangled qubits? Well, the idea is to combine mitigation and suppression in different special forms. As you know, purification protocol is just any quantum procedure that takes a number of copies of noisy states and distills from that pure state or a perfect Bell pair. So the number of input states, of noisy input states, depends on their initial quality. And the procedure to be applied to obtain a purified state at the end, closest to our target state, is also dependent. There are many different variants or forms. Today, I don't want to explore any specific purification protocol, but just a general framework about how to do this in a probabilistic fashion, because a general solution exists even if this solution is randomized. It doesn't work in a perfectly deterministic way. Well, this general framework establishes on the first step a couple of definitions. What maximum fidelity we can achieve using a protocol of this type, or conversely, what is the maximal universal probability of success for a given fidelity. The definitions are not important here. They only set the space. For obtaining the solution to this problem, an optimal probabilistic purification protocol, the tools to be used are, well, analytical on the one side, but this is not my favorite viewpoint. Analytically, the problem can be posed or can be formulated like a semi-definite programming problem. So the analytical solution can be obtained clearly in some cases, particularly when, as you know, when the dimension of the system is low. For a high-dimensional system, this is pretty hard in general. I outlined the general solution and the notation here in this slide, but again, this is not important. The main idea is that obtaining such probabilistic purification protocol is feasible and possible, and you can check the literature for doing this and finding the steps in the solution. My key observation about this solution, by the way, instead of using analytical tools, of course, you can use numerical tools for solving the system and just getting some numbers, giving you the right figures. And those numbers allow you to plot these pictures and these diagrams showing, again, what is possible and what is not possible. Feasibility is, again, a fundamental criterion when engineering aspects enter into the picture. Well, these plots show the fundamental trade-off between the achievable fidelity for this kind of systems and the success probability in doing the purification operations. So in both axes. And maybe the right side plot is more interesting as the left side one, because both correspond to a typical depolarization channel with different intensity. And on the right side, you can see something that probably know at this time, and the fact that any purification protocol, even the optimal probabilistic purification protocol, has diminishing marginal increments. So the horizontal axis goes over the number of input states, and it represents the fidelity for 3 different cases. Delta is just the depolarization probability of the channel. So from good channels to bad channels, proximally. And in the 3 cases, well, as you add more input states for the purification, of course, you can distill more information and better quality for the results. However, the number of input states grows quite fast. Even this is a little bit deceiving, because in a typical real implementation, you need even more input states than not only 10 or 11 for getting a high fidelity practically equal to 1. And it also shows something which is quite expected, that for worse channels, you need more resources. So the higher the depolarization is, the more input states you need, as anyone could suspect. But the morale and the lesson to be learned from this plot is that the number of resources, the horizontal axis, to be used for purifying or for getting good quality entangled pairs increases fast, and again, consumes and uses many of the entangled pairs generated by any type of hardware, regardless of the technology. These plots are completely independent of the technology that you are using. A complementary view of how a purification protocol works is the equivalent circuit view of the optimal purification protocol. In this case, for a system with 3 input states. And this representation is useful, again, because in addition, or as a complement to showing that a number typically high of input state is necessary, it also shows that for a circuit description, you need some number of ancillas, qubits, also to be used. Not only the states that you receive at the end of the link, but also locally generated qubits to be used or to be consumed into this process. The rest of the preparation circuit, the box V here, is just a standard superposition of the states. And the selection circuit is a permutation. In this case, 5 permutations on 3 elements. The identity permutation is not necessary and is completely omitted. Okay? So it requires not much explanation. And to reinforce this idea and to emphasize how many resources one should use to present or to implement an effective purification, we need to pay some attention onto the natural idea to use this process, which is to apply purification recursively. Why should we limit to using a single round of purification? If we can distill some better quality state, we can apply again purification, a new round, onto some number of those purified states in the first round and get even better results. So replicating this idea, instead of consuming an inordinately large number of input states, is also perfectly possible and has one clear advantage, which is delay and possibly less consumption of resources, although this idea is not completely exact. The number of resources which are consumed in total when using purification recursively, one round after another is not necessarily lower than if you use a high number of input states into a single round. So the plot again is very similar to the former one. Here it is depicted the fidelity against the number of rounds, the recursive depth that we are using. And we can observe again something which was perfectly expected. The higher the number of rounds, the better the fidelity is. However, again, as a practical lesson, the number of rounds that need to be applied grows again quite fast. In other words, the shape of these curves is again concave, diminishing returns. So every additional round improves fidelity by a lower margin than the previous rounds, and up to the point where the increase in improvement for fidelity does not pay off, just using more rounds to get a tiny enhancement of what we want to achieve. And another drawback, at least for building practical systems, is that using multiple rounds of purification entails or implies, obviously, a large delay. And worse than that, it requires memories with longer coherence times where to store the input qubits or the purified qubits from the previous rounds. So all the factors that we have been covered so far are intertwined. They are not separable and cannot be treated in different or in an independent fashion. Should we do a break, or I am allowed to go to the end? What do you prefer? No response? I'll go on. You chose. So let's move now to something which is more familiar to me, because it's part of my history, using classical resources for networking, for building networks, and how these classical resources have to be modified, possibly when dealing with quantum phenomena, with quantum physics. The typical classical resources for quantum networks have to do with metrics. We need to understand first what is a good system and what a bad system is. We have to define what a good network should offer. Secondly, we require to design network algorithms, how the elements or how the components, the equipment in the network work internally, not just from a user perspective. And third, and not the least important part, the general architecture, how all the system is organized, how all the components and all the pieces are related to each other. What is the distribution of the roles and the responsibilities for every element in our network? Architecture might seem to you an overstated word here, but it is not. When designing the network, an architecture is a fundamental idea and one of the most critical design steps. Let me start by briefly reviewing the principal metrics that we engineers use for understanding if a network is a good one or a bad one. Well, from an internal design perspective, we typically speak, first of all, about throughput. In the case of a quantum network, throughput refers to how many entangled pairs can be effectively created with enough quality between one sending point and one receiving point. The mathematical definition is unimportant here, so don't pay attention to this. The word definition is all that we need. How many entangled, the rate, how many entangled pairs per unit time can be created, on the condition that those entangled pairs should exceed a minimum fidelity. Otherwise, they are useless and do not count anymore. An extension of the throughput idea is the capacity of a network. How much information or how much content a network is capable of transporting between any original point and any destination point. I mean, the whole system capacity. Well, the capacity of a network admits a very simple definition. However, the problem is completely intractable. For completeness, network capacity can be defined as a vector, just the throughput or rate vector for any possible pair of source and destinations that can exist. As I have said, this is typically intractable as a mathematical problem, and there are only a few alternatives. One has to resort to simulation typically, or to just understand one small and idealistic piece of a network if I'm trying to extrapolate how capacity will scale or will behave in a more complex system. So capacity can be calculated only for very simple topologies. For isolated nodes or for isolated switches, that's important too for understanding how network algorithms operate. What is the regime, which is more interesting for designing that part of the network, and also for linear topologies or for ring topologies or for very structured and regular topologies like grid networks. So those examples are more academic than practical, of course, but we gain a lot of insight by understanding such simple systems in order to inherit some ideas for building large networks, and this forms a large body in the academic literature. The second important performance metric that we speak about is delay, how much time we need for establishing the effective entanglement between 2 points. Either the distribution of the delay or the expected delay, which is easier to calculate. But recently, in addition to being able to reason about expected delay, it's important also to take into consideration a novel metric which is called age of information. The age of information, in the definition it's implied, is a metric that quantifies the freshness. How old is an update? Many future and current applications in classical and quantum networks entail or involve the periodic transmission of information from one point to another. Just a simple example is in distributed quantum computing, you typically need to repeat the same operation or the same measurement many times just to extract the expected value. So for some cases, these operations need fresh generation of entanglement, because in this case, fresh is better than old, unless the system decoheres and loses the fidelity we need. So the age of information can be quantified again, just looking at some specific point in time, t, and measuring or counting how much time, how long has elapsed between the last update until the current time. Well, age of information makes perfect sense for dealing with these systems, but in the same form as delay, age of information is a stochastic process. So typically characterizing and analyzing or studying these two processes, delay or age of information, is again not easy analytically. We can draw or we can apply tools from queuing theory, which I presume you are not familiar with, but it's just a branch of probability theory for dealing with expected quantities. But the better results we can achieve using these tools are typically bounds, upper bounds or lower bounds, not exact expressions for this. So again, approaching the performance of a network from the side of theoretical analysis is rather difficult in practice. And topology, I mean complexity or size of the system, is not the only reason for that. It's because some of the metrics that we are interested in are not easily amenable to analysis. I want to stress here the importance of timely updates, of freshness of information, and not only delay. Delay needs no explanation at all. For any sort of application in a network, of course, you want to minimize the delay. You want to obtain something in the least possible time. And by the way, this is not even easy to obtain in classical networking. What is the typical delay for any communication process in the classical internet? Can you advance an estimation? If you want to transmit something all over the internet, even to your neighbor, what is the typical delay? How much? Tens of milliseconds at best, yes, which is very high. For many real-time applications, a delay of tens of milliseconds is completely unfeasible. Some years ago, it was a popular term in communications engineering to speak about the tactile internet. The tactile internet is a system which is capable of reacting in almost real time. Well, in objective terms, a tactile internet means a delay under 1 millisecond. So achieving a delay of under 1 millisecond in a network today is almost impossible. That's it. Does anyone know the reason for this? Even speculation? Well, the speed of light, clearly. So what is the distance that light can travel in 1 millisecond? Well, not much. Well, the main reason is the store and forward paradigm, that routers and switches in the internet store in their memory temporarily the bits until forwarding those bits. That delay sums up to milliseconds or tens of milliseconds or even hundreds of milliseconds. For many communication processes, this is negligible, but for many others, it's a lot and cannot be done. So again, I'm departing from the main focus of today's talk, but in the classical internet, think about controlling a manufacturing plant in real time. This requires, for instance, sub-millisecond delay, which is not possible at all today. So why do we put so much emphasis on delay? Because delay is important. I mean, reducing delay. But moreover, what I'm trying to explain today is that delay is not only the figure that matters here, but freshness of information is also important when considering a network, especially if it involves quantum networking. So if we start to aggregate and accumulate all these things together, what do we need to use for building a network capable of supporting quantum applications? On the very least, all the processes that you are seeing in this displayed figure. The capability of doing swapping at the very lowest level. The capability of purifying or correcting the errors for getting high fidelity entanglement. And the capability to finally use that entanglement for real applications. So going bottom up, you see where each piece fits, like in a hierarchy. Well, here I also am showing what channels are purely quantum and what channels are classical channels too, and how many devices are involved in this set of operations, networking devices or remote devices. But this is the summary of the fundamental tasks that we will need to implement with better performance that we have today. But this is not the solution to our final problem. Regarding classical networking resources, let's assume for the moment that the problem of creating the entanglement and obtaining high fidelity entanglement has been solved. So let's forget for a moment about that. The next problem is not only to creating and sustaining over time that entanglement, it's about choosing a path or a route for effectively doing such creation process in the best way. And here, the best way means using the least amount of resources, quantum or classical. So designing a network is not only being able to making a system work, is making the system work with the less amount of resources under consumption. So I'll be honest again here. For engineering, money is important. And when designing the system, you do not only have to fulfill some specific objective requirements. You have to fulfill that under a budget. And even if you don't believe this idea, just creating the quantum resources, distributing entanglement and so on, doing purification, et cetera, requires hardware, requires money for building the devices, requires trained people for managing the network, and so on. So using a minimum amount of resources is what makes the problem difficult in this case. So let's examine now next how we can model the problem of routing, choosing a path inside a network that, among other things, consumes few resources only. The fundamental problem is just selecting one of the many possible paths that exist. Because choosing a path is not oblivious or an unimportant decision. From a purely abstract point of view, a network is just an undirected graph formed with edges and nodes. Every node is just an intermediate switch or an intermediate device, and the links are just the communication links, classical or quantum. There's no distinction here. But on top of those links are nodes, we put the external input to the network. And the external input to the network are demands or requests. Users generate actions which the network has to implement. In our case, an abstract view of those requests and demands can be modeled as a simple tuple. A source, S, the origin point, a destination, D, the final point, minimum fidelity, F, a maximum delay, T, and a number of entangled pairs, delta. Some of these values can take a default value. For instance, if we put a delay equal to infinity, just infinite, sorry, this means that delay is not important for our application. But for completeness, the 5 elements in the tuple exist. Well, this is purely descriptive of the problem. It doesn't start to solve the problem at all. The goal of the routing problem is to implement a policy. A policy is a strategy for behavior. What the devices, the switches, and the routers have to do, and when they have to implement those actions. So a policy for the network is just a prescription. It's like an algorithm, but a distributed one, telling us what to do next, a precise and accurate instruction set about what to do and when to do that operation. For instance, a policy should specify for a network if we should do purification or not. If we decide that purification is beneficial, how many rounds, or on how many input states, and so on. And these decisions are not independent, they are coupled. So one local decision affects or modifies the next decisions to take. Once we have a policy, we can compute a path throughput, just the rate over the path, and we can satisfy a given entanglement rate. I will omit all the details here. The final piece of the complete routing problem for a network is to being able to get a description of the network, the topology, and all the remaining elements. And the final outcome should be a set of paths, a twofold outcome. One piece is the set of routes or paths to be used. And the second is the policy itself, the strategy to follow for implementing the performance metrics that we are seeking. Well, from a purely computational point of view, the problem of selecting a route or a path and identifying a policy has an exponential complexity. Any problem on graphs is combinatorial in nature, so its complexity order is naturally exponential. But in this case, it is complicated. It is further complicated by the task of finding an effective policy. What sort of mathematical tools do we have for modeling the calculation of an effective policy? Well, the problem is difficult not only because the exponential nature of any variant of problems on graphs, but also because the fact, which is not completely evident, that the metrics that we defined a few slides back are not separable. The probabilistic nature of swapping and losses in a quantum network makes that deciding when a path, a route, is good or is bad lacks a fundamental property that exists in classical networks. This requires some explanation, which is quite easy. In a classical network like the internet, if you find an optimal path between 2 points according to some metric, no matter which metric you are using or you are interested in, any part, any subpath of that optimal path is itself optimal. So optimal paths nest, are contained inside other optimal paths. That is not true for quantum networks because of fidelity and the randomness which is inherent to increasing the fidelity and the probabilistic nature of swapping. So the same principle does not work at all, and we cannot trust that a good path, which is 2 hops long, for instance, is part of a longer path, which is 4 hops long. We need to start the computation again if we modify the policy or if we modify the metrics. And this is an extremely difficult part to model. And finally, finding a policy, which is a strategy, can be tackled mathematically at least using some tools that possibly some of you might be familiar with, because the problem can be modeled as a Markov decision process. A Markov decision process is just a fancy name for something rather simple. A Markov decision process is just an assignment of probabilities to actions. It's just to have a set of actions and to choose with what probability you should apply one particular action. And the Markovian property was explained in the previous talk. So I will not review again what is the Markov property. Well, in synthesis, for a Markovian system, all the previous history is collapsed or condensed in the current state. That's the point. So these kind of systems, finding efficient policies, finally resort to finding or to solving a Markov decision process. But there are more letters in the name, a POMDP. MDP is Markov decision process. PO is partially observable because the state of the system is imperfect. You do not have typically access to all the state variables. You only know approximately how your neighbor is behaving or what action is going to apply. And this introduces an extra degree of difficulty. So the final end or the final conclusion about this is that using mathematical tools is fine for gaining insight again, but it's not tractable or amenable to analysis, easy to being applied here. Again, one needs to resort to many other different techniques, much more ugly, honestly, to understand what a good policy is. However, some progress has been made recently into formally finding good strategies and good policies for networks. It's only 15 minutes to the end. I'm running short, but I will finish in time, promise. This is just a simple example of what means to select one path or another path into a network. So entanglement relationships are distinguished by their color, and you can see different source and destination paths, and the idea is to be able to choose the correct path. This topology is, of course, not real any longer. It's just a simple grid, 3 times 3. So far from any real network, even metropolitan networks. And maybe the most interesting part is just the legend at the bottom part, which encloses some of the real physical parameters that we have today when building these sort of systems. Typical attenuation for loss in fibers is 0.2 dB per kilometer. You know this figure. The entanglement success probability rarely goes up to 1 part in 10,000. The entanglement generation rate is best to be cautious and keep it under the megahertz. And the swapping success probability is 0.5, just to give a fair and true idea of how of the operating regime on how these networks work today. I will go quite quickly about this, because the classical resources, when designing a network, even for quantum application, also involve or also need to address the need on how to calculate these routes or these paths. In other words, who is responsible of doing this sort of computation. This path has to be chosen. So the fundamental question is who is choosing the path? Is some predetermined or fixed rules installed at the switches, or there is some sort of intelligence which is governing how the network works and chooses, depending on the current state, that path? Well, there are many different options for doing this, even in classical networks too. So this is an analogy with what we are doing today. And I will only show very quickly 2 or 3 alternatives for this. In the centralized proactive routing, the idea is that the network receives the demands or requests. They are announced previously, if you prefer this view. So at the first stage, all the users announce the requests, or they do this dynamically, doesn't matter. But these requests are perfectly known in advance. This information is forwarded to, yes, a central intelligence node, which collects all the network information, all the demands, applies some very difficult and complex computation and algorithm, and produces a solution. And the final step is to install or to instruct the network devices to apply those operations. So the name is proactive because the system doesn't react until knowing all the demands. And it's centralized because this element here at the right part just is in charge of calculating everything. This is not bad, as you might be thinking right now. This centralized proactive solution is good and has advantages in a few dimensions. First, if you centralize all the information in a single decision-making point, those decisions could be optimal because the system has all the information, which is not what happens in reality networks. A second advantage is that this idea of centralizing the decisions completely decouples the network infrastructure, the devices that materialize or realize the system from the decision part. So you can view the network just as a fabric, as a large and huge switch, just receiving instructions on how to do next. By the way, this is the form in which large parts of the internet work today. A central controller takes the decisions and instructs the individual devices on what to do next, how to forward the packets, and what to do with the bits. So this is an evolution. I was emphasizing the idea of evolving networks firstly, and this mimics the complete application. A second possibility is to do the same proactive routing, do nothing until we know the demands, but decisions are taken in a distributed form. So every hop makes a local decision and decides what to do next. So this puts part of the logic into the devices. It's also similar to the form some parts of the internet have been working for decades, really. Has a very low complexity, but decisions, of course, are unlikely to be optimal at any point, because any localized information is only part of the system behavior. And a third possibility, which is included here, is about the centralized reactive routing. Differently to proactive routing, in reactive routing, the difference is that all the physical elements in the network create entanglement continuously. Remember, in the proactive approach, entanglement is not created until the demands are revealed. In this reactive routing, entanglement is continuously generated, whether it is necessary or not. And just in case a demand appears and needs to consume some entanglement, those resources are used. Otherwise, the remaining resources are completely discarded and dismissed, or waste, if this is costly. I am assuming during all this time that generating quantum resources is costly. They are not for free. Because if this is not the case, well, much of this doesn't make sense. I'll skip this part. Let's go back to consider the problem of how to perform entanglement swapping end to end, because I skipped this part just at that slide. So one thing is to understand that entanglement needs to be created. A second problem is in what order do we have to apply the entanglement swapping operations? Is there any optimal order for achieving this? Again, the design space is very large. There are many different forms. We can apply a sequential swapping set of operations, just going from left to right, the top part. So in the top panel A, first node B applies a swapping operation. Next, if successful, node C uses a swapping operation, and so on. This is, of course, not the only possibility. The drawback is delay, which is large, one step at a time. So we can parallelize the operations for swapping and arrange all those operations in a tree. Is the second panel, panel B. In panel B, nodes B and D apply swapping simultaneously. And again, if successful, node Z in a second round applies swapping and creates the end-to-end. There are even more options, which is applying simultaneously, but not in a tree fashion, or ad hoc, or heuristic approaches for doing swapping. Contrarily to what you might be thinking, the selection of the order for doing the swapping has an impact on the network performance metrics, both in throughput and in delay. The two of them depend on how you apply the swapping operations, in which order. So this is not an artificial problem, has consequences. Is there any chance of obtaining optimal swapping policies in our network? Again, we can resort to mathematics and not to just brute force simulation or just intuition or something heuristic for trying to deduce or derive the optimal swapping policy. And I want to mention here two approaches that can be used and in fact have been used at least for theoretical purposes, not for practical engineering. Because of some reasons I'll comment about in just a moment. One approach is to model the system as a control theory problem over a finite horizon or over an infinite horizon. In this case, you can set up the classical Hamilton-Jacobi-Bellman equations and solve that equations for finding the optimal policy. The problem with this approach is that the system is not deterministic. It is probabilistic and randomized. So solving those equations under uncertainty is, again, quite difficult, even numerically, in some cases because the solution is not stable. The second option is maybe not very scientific, but is very effective also. And it's representative of one set of tools that is gaining increasing popularity in the recent times. It is combining network control algorithms with artificial intelligence, specifically with reinforcement learning. Well, this is not just a brute force approach. I want to stress the difference here because the idea is to make the system learn under experience, just to try things, and if this solution works, to reinforce that solution for the next decision to take. That is the basics of reinforcement learning, as you know for sure. However, the novelty with the reinforcement learning approach used for networking problems is that originally the reinforcement learning approach used internally two different forms of optimizing the system. One is called Q-learning, and the other is gradient optimization. Well, both of these fail, are unstable when applied to systems with uncertainty. So the way out of this problem is to modify both rules. Neither Q-learning nor policy gradient are particularly efficient when you attempt to use reinforcement learning for solving any kind of network problem. The idea appeared or was proposed not long ago in 2017 by OpenAI researchers, in fact, and it's called proximal policy optimization algorithms, which are now used at almost any artificial intelligence system. For instance, many of the popular models for large language models that you, for sure, are using internally use the proximal policy optimization algorithms proposed by OpenAI. My point here is to stress that these kind of techniques also have a place into the network design toolbox. And it is an important place in the years to come. And we should not neglect the benefits of using this kind of tools also, even if these seem very different or very separated. I will skip this part, and I'll go through just a final comment, because we are reaching the scheduled time, on the feasibility of building a terrestrial and non-terrestrial network with all this technology in a single piece. How far are we from reaching that final goal? Well, the short answer is that we are still rather far. The experiments are the systems, the current operational systems that we have today are not so impressive. This picture shows running operational quantum network here in Chicago with 3 nodes. 1, 2, 3, 3 nodes. That's not a network. That's just something a little bigger than a pure metropolitan networks. Well, the main sponsor or the main leader of this effort is the Argonne National Laboratory and the universities in the Chicago area. So the span of the network is a few tens of kilometers. And what is interesting in this picture is maybe the technology, which highlights again another absolutely important fact about networks. Networks are heterogeneous. There is not a single hardware device which will push up how networks will operate. In this case, for this test bed, they used, as you can see, sources with rare earth elements, ytterbium or erbium, doped, 3 types, quantum frequency converters, and Bell state measurements. So 3 different types of hardware for building the switches and routers. And this is not by necessity. It's because networks will, in reality, will have different kinds of hardware, necessarily. On top of this hardware, they implemented different error correction techniques, including purification. These 3 panels summarize what kind of techniques have been used in the testbed. On the left part, pure purification protocols. In this case, a deterministic one, and I mean, not the optimal solution I spoke about. The second part, the second panel, panel C, is a concatenation of Gottesman Kitaev Preskill codes plus quantum LDPC codes. And the third solution, the 3 of them work at a time, is based on pure quantum LDPC codes. So once again, what is interesting about this is the combination of techniques. And the same tenet and the same principle can be applied for a new time. Building a network means integrated all the technologies into the system, not relying on a single technology, because there's no single answer that can solve all the problems. Regarding satellite networks, why are satellite networks interesting or feasible? Well, the answer is quite obvious. On space, there is no attenuation, almost. On space, we do not have depolarization. However, before getting to the satellite, we need to gap or bridge the atmospheric channel, which is full of impairments, really. So the real difficult part of a satellite QKD or satellite quantum network is transmitting effectively between the ground station and the satellite, or in the reverse way between the satellite and the ground station, not possibly the inter-satellite links, which is a perfect medium for transmission. The most famous experiment, you know this, and I'm showing this picture just for showing how simple the hardware was in this case, is the famous MISIUS experiment by the Chinese scientists. You know about the MISIUS experiment? Yes? No? Nothing? Unbelievable. Yeah? It's a BB-84 QKD system from a satellite in an orbit 500 kilometers of altitude to a ground station. The system can work with a reasonable key rate up to 1,200 kilometers, which is the world record so far for this kind of system. But in the end, if you look at the components, this is exactly BB84 on space. Just this. Is BB84 the best quantum key distribution protocol for satellites? What do you think? You think it's time to finish, and you're right. Well, let me go directly. I had an interesting part maybe for you about converting a Rydberg atomic receiver into an antenna, but I ran short of time. Maybe some other year. So let me go to the final remarks for concluding this presentation. What we possibly learned in this long talk, just for encompassing all the different pieces that form part of the network. Well, despite all the progress so far, networks need specific quantum mitigation of errors and quantum error correction, which is different, slightly different from error correction in quantum computing. So a significant part of the physical bits that will be used in our network will also be, or the resources ultimately will be also for compensating the possible errors that exist for creation of entanglement. And this will sum up a significant part of all the resources to be used. The quantum internet is not just, or will not be just a communication network. It will support many other functions, including sensing, distributed computing, and implementation of pure quantum protocols. That's fundamental for understanding why we need to employ all the advances in the base technology that you are developing. Quantum networks look beyond the communication part. In fact, as you should know, encoding information onto quantum states does not provide a significant gain in capacity for network. At most, double, which is not really so high at all. And finally, even though I did not have enough time for going into some details on this, it's exciting to see that in the near future, maybe in the next decade, we will be able to replace antennas with atomic receivers, working exactly like antennas, really. Antennas are not only are ugly, but they are very difficult to design. They require a full chain of radio frequency circuits, which Rydberg atomic receivers can avoid completely. The atomic receivers are subject to less noise sources and have a sensitivity several orders of magnitude better than a typical radio frequency antenna. So the standard quantum limit for our receiver, for our Rydberg system, is around nanovolts per centimeter per hertz, which is far beyond what a classical system can sustain. There are important challenges in building this, but this will be the topic for another lecture, maybe at some other moment. So I want to thank you for your patience and for your attention here today. And I don't know if we have enough time for maybe one or two questions.
Yes, maybe we can do one or two quick questions. And it's a shame that you didn't have time for the last part of the talk, but I'm sure if anyone is interested, you can talk to them during the coffee break.
I'm sorry for not giving you a break.
No, we still have time for the break, don't worry. So. Are there any questions?
Hello.
Hello.
Your lecture was very, very interesting, and thank you very much. I had a question. You said a very powerful statement in the first half of the lecture. It was that technologies that don't align with our existing infrastructures are not happening. And you gave the example of the existing internet and the new applications. Why is it so that in satellite QKD, the majority of active missions, or all of the active missions right now, are in discrete variable QKD, rather than continuous variable, which is in alignment with the current hetero and homodyne detectors that could be were implemented?
I believe the reason is twofold. First, most of the few experiments on satellite QKD are just feasibility experiments. They do not look for integration into an existing telecommunication network. They want to test the limits. So the fundamental answer is this feasible or not? And what are the key rates that are achievable? And I believe, but maybe some of you could correct me, that perhaps implementing discrete variable is simpler than implementing continuous variable for these kind of satellite communication systems. But for our real integration into networks, again, heterogeneity is fundamental. Both types of systems will, with time, be included into the network, because networks have been created with that purpose in goal. We do not discard any technology, even for the current networks. All of them form part. Even if you think about the classical internet and look back at technologies used maybe 20 or 25 years ago, they do exist. They are still used. They are residual, yes, but they are still used.
Okay, so you do believe that discrete variable will somehow make its way into the existing infrastructure? Or do you think it's just for feasibility and nothing else?
There have been some attempts and some experiments for including discrete variable into commercial telecommunication networks and fibers, and with success. I know, but I can't remember the details about some recent experiment in Germany that transmitted discrete variable QKD onto C-band fiber, not a dark fiber, just multiplexed with typical telecom signals. I can't remember the details. I can look for the reference if you are interested.
All right, thank you so much.
Any other question?
It's working? Yeah, okay. So thank you for your speech. And I was wondering, when you talked about the importance of the order of applying swaps, it had an influence on delay and throughput. I was wondering if there is like a favorite fashion, or maybe which one does better at what?
For implementations, you mean?
Yeah.
Well, this is not implemented.
Okay.
However, the best way of doing the ordering of entanglement swapping is in parallel and in a nested form, because it's the fastest one. The problem is that doing that requires synchronizing all the elements, all the intermediate nodes. In other words, it requires a relatively complex classical protocol for coordinating all the parts. I did not stress this idea, but many of these protocols are heralded protocols. They need classical signaling between the parties. So you need to design a specific coordination protocol for using that solution. Parallel operations for using delay, and nested one, which is, by the way, one of the first proposals for doing entanglement swapping conceptually.
Okay, thank you.
However, I have to add, just very briefly, that this works ideally. In practice, if you supplement the problem of entanglement swapping with minimum fidelity, for instance, just for looking the best path among different possible alternatives, then this modifies the problem. And using some heuristic approaches or some opportunistic approaches might work better in practice again. So if you discard all these impairments, then nesting and using parallel swapping is the best option.
Okay.
Okay, so let's thank again the speaker, and I think that further questions can be addressed. So now we can go to the coffee break and then the last session of the day, which is the poster session.